All right, 12:34, let's get started. So hi, everybody, and welcome to the Data Sciences for Biomedical Professionals workshop series. I'm Dr. Brown, and I'm excited to be here and talking about these different aspects of data. So just a couple of things to kind of note that we have going on right now. We got an email yesterday about a pre-workshop survey. If you all are interested in taking this survey, it's a part of a research project that myself and Dan, who I'll introduce in a few minutes, are working on to better create learning resources for individuals in the biomedical space for learning to work better with data and using a variety of automation programs like R and Python. So if you are interested into that, the link is also in the chat for you to take that pre-survey. We will also be recording this session so that it can be uploaded in the future. If you have any issues with this, please let us know. And if you would like to remain more anonymous, you're more than welcome to chat us individually in the chat feature so that you're not using voice or doing anything you're not comfortable with. So with that being said, does anyone have any issues with the recording? Okay, I don't see anything, so I'm going to start recording and get rolling. So I'm going to tell you all a little bit about myself. So I'm Dr. Brown. I am a computational biochemist by training, but a data enthusiast who uses data science in a variety of projects I work with here at Virginia Tech. I'm an assistant professor and a science informatics consultant in university libraries. So I work with a lot of different people all over campus to integrate bioinformatics and molecular modeling, as well as data science techniques into research projects, while also running my own lab that looks into modeling of different disease states and of different kinds of ways to engage undergraduates in research experiences. I do a little bit with health and data analytics, which is why we're here today. And I'm very big for working with data reuse and reproducibility and being as transparent with methods as possible. And I also have affiliation in the Department of Biochem and in the Academy of Data Sciences. How this workshop is going to work today is that you're going to have your main instructor, which is going to be Dan Chen, and he'll introduce himself in a minute. And I'm going to be here for helping, but we also have two helpers, Jonathan Berganti, who's a lecturer and the data bridge manager in university libraries, and Carter Gottschalk, a research assistant who will be taking notes and then able to facilitate and help people one-on-one if you're having any problems in breakout rooms that we'll put you in as we go along. So we're excited to do this in a very collaborative way, and it's one of the best ways to learn how to use different coding languages as you work with your data. All right, and now I'm going to turn it over to Dan, who is really the creator of a lot of these resources and these workshop series in general. Dan is going to talk about himself, and then we'll get rolling from there about how everything's going to go.
Okay, hello. All right, so I'm Daniel. I am a PhD student here at Virginia Tech in the Genetics, Bioinformatics, and Computational Biology program. You can consider myself as a data science educator. I've been involved with the Carpentries as an instructor and currently is their community maintainer lead. And last year I was one of the R+RStudio interns where I worked on using R to help create lesson plans and creating an auto grader system so you can submit code to get checked. And the names of those packages is Grade This and Learn R. And part of today's workshop is related to my dissertation, which is studying data science education and pedagogy for the biomedical sciences. All of the materials that we have presented are online, and so you can go to the website, which is also, it should be like pinned at the bottom of my video. And the slides are also available if you want an actual picture of the slides. Just so you know, the slides are literally screenshots from the lesson materials, so there's really nothing, the slides just make it easier to present things during the workshop. Carter is the head of, or in charge of taking notes on the Etherpad. So there is also a link to the Etherpad at the bottom of my video. And what that allows us to do is we are able to take collaborative notes. All of the links that I have provided will be pasted up there. So if you really need like one place to bookmark for today and Thursday, then that would be the link to go. It is a regular notes file, and then we'll save that off into another location, so it'll persist after the workshop. And then last but not least, if you are caught up in any of the technical jargon or technical terms, you are free to look at this project that is maintained by the Carpentries, which is a glossary of technical terms. And so you can use that as sort of your quick dictionary as we go through the workshop. So a few logistics. First, if you don't see my presentation screen, I'm not actually presenting off of a screen share in Zoom. So what you should be able to do is find me in the whole gallery of people in Zoom, click on the little 3 buttons, and then pin my video. So if someone else takes the mic, it doesn't actually pull away from my current screen. But it seems like everyone is muted, so that shouldn't really be the case, and everyone should be able to see what I'm presenting. As far as your actual screen layout for the class, think of your current computer screen. If you are, this really applies if you only have a single monitor to work with. Think of your current screen as 4 quadrants, where you have just the Zoom video as 1 quadrant. R+Studio, which we will be working on in the next hour, will be another quadrant. And then you have your Etherpad open in one, and then the participants and Zoom participants and chat in another. And you can resize them vertically as needed. You don't really need that much space for the participants panel and the Zoom chat. The main reason for the participants chat is having access to the yes, no, those little buttons. So if everything's okay so far, in the sense that you can see my presentation screen, most of the things are legible, can you use the participants panel to click the green yes, and then we'll know that people are sort of, things are working. And if you have an issue, hit no. At any point during the workshop, if you have a problem that you don't want to bring up in chat, or you're having like, my computer is totally borked, click the no X, and then one of the helpers will be able to help you figure that out.
All right, and for everyone just joining, we're excited for you all to be here. We've got a couple links that where we'll repost in the chat right now for you to get acquainted with things and have access to our resources with our lesson materials, slides, and a collaborative note space. With that, though, we'll kind of get rolling from there. Does that sound good to everybody? All right.
Yeah, and the main takeaway is the 2 links that are pinned at the bottom of my presentation video. Those, if you ever get lost, just go to either the Etherpad or the main materials page, and that should take you to any of the links that you may have missed during in the actual Zoom chat. So this series of workshops is actually part of a research study, and from the overall findings that we got, where people are sort of indifferent about using a programming language, working with their data. They are not really programming in general while they're doing their analysis work, which sort of makes sense why they're sort of indifferent towards it. But they have this strong belief that they need access to their original raw data set to be able to do a repeatable analysis. And so this is sort of the gaps that we're trying to fill in this series of workshops. This is really just the first set of introducing us into the world of programming for data analysis. And so we're trying to bridge that gap between you wanting to work with your raw data set, but you either don't want to or don't have the skills, or you're trying to learn all of the skills for programming off of that raw data set. And the study actually created a set of personas that you can read more about. It's on the actual main workshop page. And so as our first exercise, just so we can sort of deal with any problems right now, but also for people in the chat to sort of know each other, go to the personas page and sort of talk amongst yourselves with which actual persona do you most identify with? And I believe breakout rooms were set up for this. If not, eventually they will.
We have breakout rooms, so you guys can take a look at who you most identify with for personas and go to the breakout rooms. We'll go there for about 3 or 4 minutes and then pull you guys back in as we keep moving forward. Look at me go. I made breakout rooms.
Oh yeah, I was gonna say, I thought I don't see the breakout room, so I don't know how they're made. Were
I
they
didn't
just
assign.
4 rooms that
Yep.
were those 4? Okay.
There's 3.
Originally,
I put 1 and 5 in one of them because I couldn't do the math fast enough.
oh, but so it's are they all random or were they
Random.
labeled? Oh, okay, cool. Okay, that's what I, because when you described it, I thought I was like, wait, did you label them and then they're supposed to self-assign, or are they just gonna talk amongst themselves?
Hey, the notes thing, it says I was typing too many messages and it's limiting me and disconnected me. I don't know what to do with that.
Really, on Etherpad, it rate limited you?
Yeah, and for some reason when I'm typing, it's coming up in like pink highlight.
Yeah, that makes sense.
Okay, yeah, it did. It said you were limited, and then it disconnected me. I refreshed, so it was fine. But just note if there's like a delay in what I'm typing on the notes, that's why.
Oh, that's interesting. Yeah, so this isn't. So I was trying to originally make the Etherpad through the carpentries page, but then there's a very big blurb at the top that says, "Don't use this for your own work." So I was like, "Oh dang, that was unexpected." So that's why it says Wikimedia, because it's like that's the more public one, and I guess they have a stronger rate limit to it. And then for the next time, which is probably not going to be on Thursday, we'll see how bad or good this is doable. If it makes it easier for you, you can put in a text editor and copy paste things over if you get super rate limited.
Okay.
But I might try to figure something out. Actually, I don't know if I have time. It's not going to happen by Thursday, but for next time, I might just set up my own Etherpad server, and then we can deal with it that way.
Okay.
Is it your actual? Oh, actually, do we have a timer going on?
Yeah, about 1 more minute.
Okay. Yeah, we'll see. Just let me know how badly you get rate limited.
And when they come back, do you want to ask if anyone wants to put in the chat what their persona is or talk about it?
Yes, I will just ask them to. Give me a second.
All right, closing the rooms.
Okay. So welcome back. So if you would like,
2 more rooms
please
waiting to come out.
No.
All right, there we go.
Okay. So welcome back, everyone. If you would like, just type in the name of the persona that you mostly identified with. It's actually kind of interesting to see who's actually attending the workshops. Just a little bit more background about the personas. They are really just fictional characters that are representative of of a audience. And so it sort of helps direct and pinpoint like the actual content that gets created for the series of workshops. All right, so between today and Thursday, we will start off with learning about some of the basics of spreadsheets and when they are useful and how to use them more effectively. And with regards to the personas, yes, there's definitely a bunch of overlap between them. And so, yeah, they're not any one person's going to be completely relatable to only one, but it sort of gets a better sense of the group as a whole. Okay, so between today and Thursday, we're going to start our learning process. And pretty much for most of the people that in our original set of surveys where we created personas, there was a large group of people who actually didn't know how to program. And so you'll either be somewhere towards the beginning or somewhere around this, this first slope. And the point is that, yes, there is going to be a learning curve, and after a certain point, you are going to realize that, like, okay, I've know enough to start doing my own work, and then you start realizing that there's actually a whole other world of stuff that you don't know. But there's communities around R and programming and in the biomedical sciences to help you all learn this stuff. And even me today, I sort of am on this very far end where I actually just know what I don't know, and I'm okay with it. But with experience, you are able to pick up and learn that other new skill without worrying about like the actual like syntax of the R language. So it really does take time, and just know that there is a community to help you progress and learn when you get stuck. And so, speaking about getting stuck, the debugging process, this is something that everyone, myself included, goes through. And one of the things I usually tell my students is she always asks, like, how do you know how to do this stuff so quickly? And it's literally because I probably have done a lot more screaming and cursing than she has. And so the debugging process is it is a process that everyone goes through, but hopefully at the end, when you do end up with a result, it keeps you motivated to keep going on. And so just as the final reminder that, yes, there is an entire community behind all of this, all of the materials that I have, including the artwork that I'm presenting, these were all created by people in the R community. And so just know that we all are all there to help you learn this material. And so just for the expectations for today, and it's really going to be today and Thursday, there is a lot to cover under a very little amount of time. And so the expectation is I don't expect you on Wednesday or on Friday to go into your lab or, you know, start doing your entire analysis in R right away. It is going to take time, but hopefully at the end of this 2-day series, you get a better understanding on how to curate your data. Even if you never program with R afterwards, when you're setting up your next data set, hopefully you pick up some of the tricks and tools and methods. So if you do hand off your data set to someone else, they can actually help you process your data. And as you learn more about R, you can now have a more meaningful conversation with the analyst, or by doing some of the analysis yourself, since you might actually know the domain better than the analyst, you can have a more meaningful conversation. Okay, so with that, we can start our first chapter on spreadsheets. Okay, so spreadsheets. Hopefully everyone has a spreadsheet program, whether that is Microsoft Excel or one of the free and open source versions, LibreOffice, or I think it's called FreeOffice is the other one. So hopefully you have some way to open up a spreadsheet program. And the first exercise I have for people is here are 3 potential patients, Denna Doom, Priscilla Holding, and Anya Warner. And you are taking vital signs during a randomized controlled trial, and so you're monitoring their vitals. So in the spreadsheet, what I want you to do is take those 3 people and input those values into the spreadsheet program in any way, shape, or form. And I would even say it doesn't even have to be one sheet. It can be multiple sheets. Just pretend that you are there to collect data and then enter these data points. We'll give you about 3 minutes to work on that. And when you're done, click the green yes check mark. Oh yes, I forgot to mention, you can always use Google Sheets if you don't have the an actual like program to do this work in. So if you're still actively working on this exercise, can you just put a red X so I can tell if the people who don't have green checks, if they're still actively working or they're just not actually doing it. That's fine if you're not actually doing it. I just need to know if I need to move on to the next portion. Okay. So I'm going to clear all of the Zoom participant responses and go through a few potential solutions for this exercise. So one of the first things that we could have done is take all of the numbers and put them into the corresponding column, right? So without any notion of any units or anything like that. So for example, we have a column called name and we put the person's name in, we have a time, we have their entire blood pressure in one column, their heart rate in another, et cetera, right? And so one thing to think about when you are entering data sets is certain units are going to be understood, like heart rate is probably going to be beats per minute. Same with your respiratory rate, et cetera. But then you have the notion of like, what unit is temperature being measured in? And so, yes, there is a quick way you can check by saying that like, well, if the temperature is above, essentially 40, we can assume that that is a temperature being read in Fahrenheit, not Celsius. But that is something that you want to think about. It's going to be pretty, one of these days, you're going to have a data set and you're going to have temperature ranges from like in the 30s up into the hundreds, right? And that is another data processing step that you're going to have to deal with. So especially if you are curating your own data set, that is something that you want to be able to think about is what units is this information encoded in? And so one way we can fix that is we can literally put the unit information straight in our column, right? So we can say pulse ox is a percentage, so we can say 98%. We can say temperature, this is 96.8 F, and we can put the actual unit information in there. But now, one of the things when you are working with data sets that you want to keep in mind is each cell in our data should only contain one bit of information, right? So for example, even if we look at blood pressure, we have the systolic and diastolic pressure all in one column, right? So the whole thing is a blood pressure reading, but there's actually 2 bits of information in there, right? So if our task later on is to like, what is the range of systolic blood pressures, we can't actually do that very easily without going through more of the data processing. Same with temperature. Now that we have put temperature in the unit itself, in that value, that column now contains 2 bits of information. It contains the actual value, and then it also contains the unit, right? So it would be good to, if, for example, we do have a scenario where we might be mixing Fahrenheit and Celsius, you could theoretically filter your data set based off of Fahrenheit and then calculate an average, and then filter your data set on Celsius, do the conversion, and then add that to the average or something like that. Because as it stands now, you can't really just pull the values in a column and do something with it because there's 2 bits of information that you need to be able to work with. And so again, keep in mind that when you are assembling your own data sets, each cell should only contain 1 bit of information. And so just to go on with that, what you can do is then split the name into more pieces, right? So just by creating more columns isn't really an issue if it makes sense, right? So, before we had our name in one column, but now we can split it out into 2. And somewhere in this example, I believe I also split out the temperature reading in its own separate column. One thing that you can do is place the unit information in the column names themselves, right? So we can be really explicit and say blood pressure is a BPM, heart rate is a BPM, temperature is an F. And that way, if you are entering data manually, you can sort of understand that like, okay, this column is all Fahrenheit and I don't need to worry about Celsius. And if I am working with someone who works in Celsius, then they would know to do that conversion before they enter that value into the data set, because that's sort of what that column represents. You do want to be careful when you add a lot of information or special characters in the column names. That is something that you want to be able to to work with. Like, for example, the percent sign is really like a special character. You sort of want to avoid those. In general, if you do have the ability to create your own data sets, I would highly suggest you keep everything in lowercase. And if you need a space, you use an underscore. And we'll see more about how that plays in when we start reading these things into a programming language, because the underscore actually, the space actually is one way programming languages separate terms. And so it won't understand like heart space rate as one term. It's going to understand heart as a term, and then you gave it a second term called rate. That's sort of why sometimes when you get data sets, why are things like they have dashes and underscores instead of spaces? Because visually, without having the space and having capitalization, looks nice. But as soon as it gets read into a computer, now you have to make sure that you type in a capital H for heart rate and not lowercase h, because that matters. Now you have to know that this is a space, and then you have to write extra characters to tell it it's a space for one word versus a space as a delimiter. There are sort of conventions that people sort of migrate towards, which is keep everything lowercase and use underscores. But that will vary depending on different systems that you use. But that is something to keep in mind when you're putting together your own data sets. And so one possible solution that isn't perfect is, we have diastolic, systolic separated out into separate columns. We have heart rate and respiratory rate. These column names are all lowercase with underscores instead of spaces. We have a temperature column, and then we have a separate column for your Fahrenheit or your actual unit, right? And this isn't going to be perfect. There's no such thing as like a perfect data set, especially if you're curating it on your own. But it is something that I think about because I know what the next series of steps could be. And so I'm going to prevent myself from work later on by sort of handling the data input as nicely as possible. So there's less cleaning involved later on. And so the main takeaway here is really only put one thing in each column, right? So every cell in your data set should really only contain one unit of information. And the more you sort of separate that out, the more flexible your analysis pipeline later on can be. Okay, so another exercise in the same, we'll build off of the example that we just had. Don't worry if you don't have to sort of swap your data sets around to any of the quote unquote better examples. But let's say you have 2 more readings. So you have a reading 12 hours on the same day, and then another reading taken 24 hours on the following day. And so let's take another 3 minutes to go through entering that set of data into your spreadsheet program. And again, put the green, put the green check mark when you are done. I don't know where to put this thing. I'll just keep it off the side. And do put an X if you are, if you need help. And if you have any other questions about what we just talked about, you can totally mention them in the chat as well. So let's talk through some of the examples for this question. One possible solution that you could have is you create a separate table for each patient, right? So you can either have in as a separate sheet all of the values for Gemma Dune, or in a separate Excel file for each of the 3 patients that we have. And so actually, I realize I understand why that screenshot looks all the same is because that table doesn't actually read off of a data set. Anyway, so there's one way that this would make sense. Let's say that your study is completely individual patient focused, in which case it would make sense to have one separate file or one separate sheet for each person that you're working with, right? It makes it really easy to essentially make sure that the data for each patient is collected properly. It's a little bit easier to go back and check if something was done. If you are just looking for specific values for a specific person or to compute some sort of statistic for one person, it becomes an easier task. So that is one way that you can set up this data set is you have one table for each person. The only downside is if you do go this route, if you need to start saying, for example, what is the average heart rate for all of my patients, then you have to realize that then there is going to be a data step where you combine all of your data sets so you can do that step. So the main takeaway here is as long as you have some rationale for how you're going to set up your data set and then understand that later on you need this one other step, then you're okay. Another thing that's more common that I see in Excel when working with spreadsheets is instead of creating a separate file or a separate sheet for each person, you start using white space as a visual separation between groups, right? And so you can see, let's say, for example, one way you could have done this is you have one person in one set of data, and then you have another visual break somewhere to designate another person. And that has the same benefits as before in the sense that yes, you're easier to see if I'm expecting 5 values for each person, you can count 5, 5, 5, or 3, 3, 3. You can still do your little one-off calculations if you need to. But then the only issue is when you start working with this data set, you have to deal with these blank rows if you start loading them into a program. And also this type of formatting sort of makes it almost too easy to make these one-off calculations off to the side. You can see, for example, let's say I make a calculation of the average diastolic heart pressure for Anya, and I make that calculation underneath her values. It's almost too easy to say oh, now I want to calculate the average for everyone, and you pull that whole column. Now you have that value in that column already. And so you want to make sure that you aren't really doing these one-off calculations to the side, because that is then part of that rectangle that is your data set. So another way you could have done this, and this is sort of instead of stacking your patients one below the other, you can stack them sort of next to each other, essentially a column-oriented formatting. And that sort of solves the problem in the sense that I still have my people by groups. The first 5 columns is Dena, the next 5 columns is Anya, et cetera, et cetera. And I'm not using white space as a delimiter anymore, but then I still have the benefit of checking values and stuff like that. The only problem with this notation is you're going to have definitely repeated column names if you follow that kind of formatting, which can be a problem later on. So let's say you want the first name column, you'll get 3 of them back, or some programs don't even allow you to have duplicate column names. So that might be a problem later on when you're trying to work with your data set. And if you paid attention to the news within the last month, the people in the UK got into a lot of trouble doing this type of data formatting, where they started putting data into a column-oriented format, and they literally ran out of columns in Excel and lost a bunch of patient information because of that, right? So be mindful when you start thinking about adding a lot of columns. So that sort of is related to that first exercise, where it's like make as many columns as you need. That's still true, but you don't want like groups of data stored in columns in that format. So there is sort of a distinction there when you're putting together your own data set. And so one way that sort of I would suggest you work with your, like when we're creating that raw data set that we can do our analysis from, remember that little like Likert scale that that I showed you from our results. One way you would do this is sort of take that format that I presented in exercise 1, and then just continue on entering values in that order, right? So for me, I sort of pick like chronological order for like day. And so what this will allow me to do, like even in Excel, I can use Excel or any spreadsheet program to do some kind of formatting or filtering that way. If I need to, sort of sort by first name and last name, I can still kind of do like visually see if I have the correct number of people for each group, et cetera, et cetera. But this is really the format that really, like if you try to load it into any piece of software, like this is the format that it needs. There aren't like extraneous white spaces around. I don't have repeated column names because I'm not stacking my data column wise. They're all stacked row wise. And then I have pretty much like one unit of information per each cell. Right. And so the main takeaway from the first 2 exercises is, as long as you have some rationale for the way you're setting up your data in the beginning, and you have a plan for how to deal with it later on, there really isn't a messy data set, right? Like we get messy data sets because it's usually like someone else's data that they give us, and they didn't account for different things. And so now we have to go through the process of like extracting out values, getting rid of units, stuff like that, or converting units, et cetera, et cetera. And the other takeaway is, yes, always pick the data format, especially if you're manually entering data. Pick the format that makes your manual data entry easier. And then on Thursday, I'll show you, like, as long as you have a plan from your manual easy data input, there's very quick ways to get it into a format that you can actually start doing the analysis with. Right. And so the last exercise really is, okay, let's say I am asking you to identify bad, quote unquote, bad values, right? So blood pressure greater than 140/90, resting heart rate greater than or equal to 90, your respiratory rate's over 20, your pulse ox is under 95, your temperature is over 100 degrees, any one of those values. How would you just take the data set that you have now that's in front of you, and then how would you mark that information? And so we'll take 1 minute, since there isn't really too many like bad values. So just put a green check mark when you're either done with the exercise or you're just waiting around. Click the green check mark when you're ready for me to move on. We'll put it that way. But I'll give everyone about a minute. And so this exercise is really focused around, we have a data set and we know that there are like values that we need to look into. How would you actually flag those values or those observations for within our data set? So one way you can do this is literally color code the values that are bad. So in this example, any of the values that are bad, I can flag with a red color, for example. Or any of the values that are good, I can flag with a green. So spreadsheet programs usually allow that. So the problem now for that particular observation or value that is bad, we sort of violate like that first rule of each cell containing one bit of information. Because let's say, for example, in my use case, like this 142 diastolic pressure, that is a bad value and I'm coding it red. And so now that 142 holds not only the value for the blood pressure, but also the fact that it is a bad value. Who values two things wrong, two things encoded in that particular cell. One thing that I've actually encountered in the past was I've encountered a data set where the color red was how the data set denoted a negative value, not with a minus. Loaded that data set in, I don't really see red as like all I see is the actual number. And this was a negative number other than the fact that it's red in the label. And so sort of the extreme case of what can go wrong when you put too many bits of information in one cell, it makes the data set less portable, but it also, you have to now do additional work to take apart all of those bits that's being encoded. Have only two rows that have values that need to be reported. And then what I can do is use either the spreadsheet system or in R, and I will show you how to do that in the next hour, filter all the rows such that the report cases needs to be yes. And then you can get a nice, pretty report. And this makes it better because now I can filter my data set very quickly and then write out another data set that's essentially like, these are all the values or people that need to be, you have to send an adverse event form for. And you're not relying on just colors because you might, like, colors can be taken out or removed. It's really easy to select all and remove all the formatting, in which case you've lost that bit of information. This way, the actual flag of whether or not that case needs to be reported is actually part of the data set itself and not like some visual artifact that you're looking at. And so the main takeaway is treat your data set as an actual piece of data, not as an actual data visualization, right? So adding things like color, adding spaces, that all are you working on a spreadsheet program and trying to use the spreadsheet program to give you as much information in one go as possible. But in that case, that's what visualizations are for, not actual data sets. So data sets are used to create the visualization, but don't treat your data set as the visualization itself. And it's hard if like Excel and spreadsheet programs are the only thing that you've ever worked with, because that sort of enforces and encourages you to use your data set as a visualization tool because it's always in front of you all the time. But as you sort of move on, you'll realize that if you treat your data raw as its original unaltered form and you create the visualizations from it, your data set and your analysis is going to be more portable, and you don't run the risk of having too much information encoded in a data set that needs to get taken apart later on. And you also don't mess with the actual raw data set. And so you can have your data set update and then run your entire analysis pipeline and end up with your visualization. You can imagine, like, let's say you go through this whole process of like flagging individual cells, and then you get another data set that replaces the old one. Now you have to go back and flag it all yourself again. And so that's also a lot of work because you're modifying the raw data set directly. And so the last thing, this isn't really like an exercise that I'll have a break for, but let's say you examine the patient and you ask them like, why is their blood pressure so high, and they're like in the room like doing yoga, right? And so there's always going to be like some kind of column that's really just like bunch of notes that essentially just say like a patient was just doing yoga. That's why this is not really an adverse event, even though it met like SAE or AE like results to report. Right. So that's all we have for the first unit on spreadsheets. So just as a summary, spreadsheet programs serve as a graphical user interface to one's data. It makes that really simple that like we can see the data set and point and click and interact with it. These GUIs are very convenient, but they come at a cost of flexibility, because when we try to load that stuff into a programming language to do more analysis, then we have to deal with all of the one-off calculations, the spaces in our tables, stuff like that. But when you're putting together a data set on our own, it is one of the most convenient ways that we can input data. So if we're trying to collect data, like we want that process to be as frictionless as possible. And so spreadsheets do have a place for that, but just be mindful of the next steps when you're working with your data set. Okay, so let's take a 5-minute break, put up a 5-minute timer. And if you have any questions, just let us know, but we will just reconvene in about 5 minutes. Next thing is if we now open up RStudio, and if we look at the contents of our folder that we just unzipped, this is really just a comically large version of the files that's in that thing that we downloaded. The first thing that we'll see is a RStudio project folder file, which says .rproj, and then we have a folder called data with all of the data sets that we'll be working with. I wouldn't worry too much about the other 4 files. That's really just trying to get things working over the internet type of files. The first thing I want to talk about is this RStudio project file. I believe if you have RStudio installed and you double click an R project file, it will open up RStudio using that project file. Another way you can get to this is the little files panel in the bottom right corner. By default, it opens you up to the home folder on Windows. If you're on a Mac, you can directly go to the desktop folder. I don't think desktop actually shows up in here on a Windows machine. No, it doesn't. On a Windows machine, if you actually want to navigate to your desktop, or if you realize that your folder is not showing up here, you can click the 3 buttons on the far right side from home, and that'll open up what you're used to seeing, which is this Windows file explorer, where you can then go to desktop and then select the ds4biomed-learner folder, and then you can hit open. And then that will open up the contents of that folder for you in the bottom right corner. And from here, if you navigate to a specific folder or that represents the project that you're working on, and you click on the R+RStudio button, it will prompt you if you want to open this up in an R+RStudio folder. We were working on a file before, so it's going to ask me if I want to save my changes. I currently don't. And then what's going to happen is, depending on how you have your global settings set up, it might just throw you into a brand new slate instead of having previous files open. But the most important thing is this top right corner now should say something like ds4biomed-learner. And depending on how many folders you name exactly the same, this name right here should represent the name of the folder that we are in, or really where this R project file is. And so this is what's known as working in an RStudio project. This is specific to RStudio, the program. So another mental model that you have to think about is R, the programming language, is what RStudio uses to run the program, and RStudio is really a separate thing that runs R code. And so a project really sets what's known as a working directory for our projects. And so that becomes important when we want to load in data sets, because we have to point our program into a very specific data set, and we want to tell R where that data set is located. And so that's where a working directory comes into play. How do we create a brand new R project if this is something that you on a folder on your computer and you're going to say, hey, I actually want to use an R project for this folder? What you can do is click on the top right corner, click New Project, and you can create a brand new folder that is essentially the same thing as right-clicking, going to New and New Folder. And you can click on New R Project, give it a folder name, and then the location of that folder. And if you do that, it'll create a brand new folder on your computer already having the R project file, and then you're ready to go. The other option is clicking Existing Directory, and what this allows you to do is if you click on Browse, you can browse to a folder that you already have set up. Maybe you're working on an existing project with a few Excel files or something, and you can turn that into an R project folder by navigating to that and then clicking Create Project. At the end of the day, what's going to happen is the top right corner is going to change to that project. And then usually if you're opening a project by default, it'll also change the bottom right-hand corner, which shows you all of the files in there. So you don't have to keep jumping back and forth into the little folder view of all your R files, or of all the files in that folder. And if you end up working with multiple R projects like I have here, like a bunch of my stuff, and I'm pretty sure Anne is very happy to see that there's a bunch of dissertation projects. And so as you create multiple files on your computer, or multiple R projects on your computer, it sort of will create like a short list, and you can clear this project list if you want. So, and all this does is, for example, let's say I want to jump into my a different R project folder, it'll now swap to that project folder. And then this is one way of sort of separating the different projects if you have multiple projects on your computer. And the most important thing when you start RStudio is look at that top right corner and making sure that where you think you are is actually where you are. That will save you a bunch of headache. Okay, so now we're going to go through the process of loading data into R. And if you've used R before, you might have heard of tidyverse. If you've never used R before, but you hear people talk about R, you also might have heard the term tidyverse. Tidyverse is what we're using in this set of workshops, and it is a collection of different packages that work together to solve different problems in the data processing pipeline. And tidyverse is really the short name for all of these other things. And so as represented by all of these other little hexagons and hex stickers. And so what's nice about this is if we want to use the tidyverse, we can just say, hey, I want to use tidyverse, and it will automatically load up all of these other things instead of having to load up all of those other small components one at a time. And so before we are able to actually load up a data set into R, we need to be able to find our files, right? And so before I mentioned this concept of a working directory. And so when we're working in RStudio, the working directory is defined by where this .rproj file is, right? So we clicked on that .rproj file, it'll open up that folder in RStudio, and then wherever that file is, so in this case, it's going to be in this ds4biomed folder, that is our working directory. If you're on a Windows computer, your working directory, this ds4biomed folder, is going to be under, in my case, C drive, users, Daniel, desktop, ds4biomed. You'll notice that the first thing that you see is going to be C:\\. If you're on a Mac or a Linux machine, it's going to be a / as the base, the start of your computer. And it's going to be / users, Daniel, desktop, ds4biomed. And so if we're thinking about a working directory, we can specify it using this address, right? So every folder has an address on your computer. And so this folder's address is going to be users, Daniel, desktop, ds4biomed. And so if that is our working directory and we have this data set in a data folder, so for example, this medical data tumor growth, there's two ways we can actually refer to that data set. One is known as the relative path, and the relative path stems from the working directory. And so if we already know our working directory, so think of that, another way you can think of that is our starting point. How do we get from our starting point to this data set? We can simply say, from our starting point, we can go to the data folder and then the medical data _tumor growth.csv file. Another way we can specify this data set is its absolute path, right? So instead of just saying go to the data folder, go there, we can actually say something like go from the C drive to users to Daniel to desktop to ds4biomed to data, and then that's our data set. Both
ways of specifying the file point to the same exact file, but the relative path, because RStudio sets the working directory for us, if we give this folder to a coworker or it's on a different computer, the relative path is the same, right? So like if I go to the Starbucks that is literally a block from my house, I can say like, well, exit the building, make a left, right? Versus me saying like, hey, the Starbucks is on like 27 like Old Dominion Road, right? So there's two ways of specifying the same exact thing. In general, when we're trying to work in a programming language and referring to data sets in a folder or in a project, we try to do things in a relative fashion, because we can just say like, hey, coworker / colleague, or my brand new computer because my old one just blew up. You can run this code because I specified everything relatively, instead of, maybe your coworker, not all of your coworkers are going to have the same exact name as you, or maybe your coworker is on a Mac and you're on a Windows machine, and the difference is literally the first character is going to be different, even if they have the same name as you. So that's sort of the concept between why a RStudio project exists and how it can sort of help you in working with different files. And so let's say our working directory is now in this analysis folder, right? So let's say we just took our previous example and we don't want all of our code in like one folder, right? Like we've all seen that project where like we double click it and all of a sudden like our computer stutters for a second because that folder so happens to have 500 files in it, right? And there's no rhyme or reason like why you couldn't organize this stuff into a subfolder structure. And these folders can be, if you can access it on your computer, chances are you can access it the same way in RStudio. So like cloud services like Google Drive, if you have the Drive sync onto your computer, or Microsoft, whatever the Microsoft version is, or Dropbox, those are essentially like a special folder on your computer. And if you can navigate to that folder in this like structure, you can point R or really any programming language on your computer. So treat those special synchronization folders as a regular folder on your computer. You just have to be careful if you're using like Dropbox sync with like your bunch of people, that other people don't start editing the same file or swapping the data sets underneath you as you're working, because it's shared across everyone. But that's a synchronization issue. So back to finding our files. Let's say now our working directory is in this analysis folder, right? We've sort of done some weird things and we're not using the default R project folder. Let's say our actual working directory is this analysis folder. And now we want to point to our data set, right? So before we can just say, well, our base folder was this ds4biomed, and I can just go straight into the data folder. The problem right now is if we're in the analysis folder, if we say go to the data folder, well, the analysis folder doesn't have a data folder in it. The data folder is the analysis folder's sibling, not like in computer lingo, it's like not its child. So it's not something that's like a subset of. And so this is where you see people use these two dots. In programming lingo, the two dots refer to the folder, one folder up. And so for us, if we're in the analysis folder and we want to go to the data folder, we have to say ... and then data, and then the medical tumor growth data set. And that's how we can refer to it. Or we can always go to the absolute route where we type everything from the beginning. But again, there's problems with that because, not everyone has the exact same folder structure as you. Not everyone is on the same operating system as you. You can even imagine if you have access to a cloud server or a supercomputer, your username on that computer is not going to be the same username as your desktop computer or laptop that you're working with. And so relative paths are usually more stable when you're trying to share your work. But if it's really only you working on this one machine, then an absolute path will work as well. So for the first exercise, and you can paste this into chat when you have a solution or keep it in your head. Let's say we're currently in the chart review, analysis folder, and we're working on this demographics.r file, and we want to point to the patients file in the RCT folder. That's question number one. And then we also want to point to the patients file in the chart review folder. So write the relative path for the one in the RCT folder, and then write the absolute path for the one in the chart review folder. And I'll take about 2 minutes to work on that to catch up on questions that anyone may or may not have. Okay, so the relative path. If we're in the demographics folder, in the analysis folder, notice that we have to go one folder to go into the chart review folder, and then one more folder up into projects before we can then go into the RCT folder. And so the syntax for that would be ... because the ... refers to one folder up. So the trick is you can chain together all of these ... slashes if you need to refer to a folder that's higher up just to go down another folder. And then for the absolute path, we can start with this slash. And just, again, as a reminder, this slash, in R, you can use this / in Mac and Windows. This will work. Just so you know, in Windows, if you do end up, for example, like in your Explorer and you click this button and you're saying like, I want to go here, Windows uses a different type of slash than computers are used to seeing, like the rest of the world. Like Windows is almost like the United States in terms of units. And so usually copying and pasting things from this part of the Windows Explorer doesn't work in programming languages. It will work in other Windows things, but as soon as you try to use it in a programming context, you essentially will have to either type 2 of these slashes for every one of the slash, or replace the slash with the /. So the one to the left of the right shift key, not the one above the enter key if you're on a US keyboard. So that was the main point. In Windows, you have to either double up on your slashes, and then in R, you can replace them with this /. All right, so we have all of our data sets. I showed you how to open up a R project file. So we should, right now, be in an RStudio project by looking at the top right corner. So if we navigate to this ds4biomed -learner folder, click on ds4biomed, it should show up in the current working directory. All right, so I am not going to do that. I'm going to go through this exercise with you. Whoops. All right. Okay, so now that we're in RStudio, how do we actually load up a data set? So we can open up RStudio, go to the top left corner, and go to File, New File. And we can start writing our first bits of our code to load in a data set. So like I mentioned before, we're using the tidyverse set of packages to work with libraries and data in R. And so the way we can do that is if we type library tidyverse, and I'll paste this in chat. If we type this and we have this line, have the cursor on the line and or have it selected, we can hit Control Enter, and you'll see R will take that code, run it on the bottom, and then execute that line to load up the tidyverse in our computer. And you can see like I have a few warnings because I very recently updated R and not all of my packages and stuff like that, but that's not too much of a problem. So once we have tidyverse loaded, we can use a function called read_CSV to load up a CSV file. So this is what's known as a function in the tidyverse. So read_CSV and then a set of round brackets. And then read_CSV actually does a lot of things for you. But the simplest way to load up a comma separated value is to give it the location of the file you want to load, right? And so remember, we're currently in this ds4biomed-learnr folder. And if we want to load up a data set in the data folder, we can click on data and we can click on spreadsheets, for example. And then we can, for example, say exercise. And if you start typing the first couple of characters, if you start typing like data / spreadsheets and you hit the tab key, it will try its best to autofill and guide you through picking the right folder. Another thing you'll notice is just because I started clicking into files here doesn't necessarily change my working directory, right? So that's one thing that you have to keep in mind. Like just because you see something in this bottom right corner doesn't exactly mean that's where R thinks you are. So if we go to data / and we hit tab, you can see it's trying its best to help guide us. And we can say, okay, now open the spreadsheets folder, now hit tab, and then we can pick any one of these exercises. So I'm going to pick the 010-0501. And so once we have that, this is again a relative path to that data set. And we're passing this relative path into this read_CSV function. And now if we hit Control Enter, this is that very first data set that we had in our first chapter. And so this is the made up values for Gemma, Priscilla, and Anya. And we've officially loaded this data set into R, and we can see it. The problem now is we've told R to load up this data set, and then R threw it away because we didn't really save it anywhere. Right. And so what we want is the whole reason why we're using R is so we can load a data set and then we want to be able to work with this data set. It wouldn't make too much sense if we want to do 10 steps on this data set and each one of those steps we had to reload in the data set again. And so we can save these values into a variable. And so what we can do is we can give a variable any name that we want. So I can call this spreadsheet_df. And so this is where having underscores matter, because if I did space df, it's going to interpret that as two separate things, which R won't understand what to deal with, work with. And so we're going to use _df. And then we're going to say that variable, did I spell that right? Yes, that variable will get the contents on the right hand side. And so if we want to say get, we do this funny operator that's less than and then the dash. So it literally looks like an arrow. Just to teach like good programming best practices, I would make sure that you have a space on both sides of this arrow operator, even though it's 2 characters. You don't want to accidentally refer to this as a minus sign for whatever reason when you're looking at it. And then what we can do is copy and paste the line that we just had from before and paste it to the right hand side of the arrow. And now if we run this, you can see that R no longer dumps out like the contents of that data set. And then on the top right corner, you'll see that the environment panel updated. It gave us spreadsheet_df, and it gave us some information. It's got 3 observation and 10 variables. And so we've officially loaded this data set up into R. Okay, so one thing that you can do is once you have this data set loaded, you can literally click on the words spreadsheet. And what it will do is open up the spreadsheet viewer on your R+RStudio console. And if you want, you can, R+RStudio has like this sorting ability. You can search for things. You can do this filter things very similar to basic things in Excel, but this allows you to literally just look at your data set to make sure, most importantly, that your column names got read in properly. So the question was, if I'm going back into the same project multiple times, do you need to load each data set, or does it load automatically? So if, for example, because of how I set up my global options from like tools global options, if I turn off, like if I go to a different RStudio project, or if I turn off RStudio and I like load it back up again, the environment panel here is going to be empty. And so what you see in this environment panel is like what data sets R knows about, or what variable R knows about. So if you don't see it in this top right corner, and you can click this little refresh button, if you don't see it there, then R does not know that variable or data set is loaded in. And so you would have to rerun all of that code again. And so yes, the process that we're doing right now is creating a R script that we can run from top to bottom. And now if we run these commands from top to bottom, it'll reproduce those results. And if you want to run everything from top to bottom in one go, you can click the little source button, and it'll just take everything from the top and run it all the way to the bottom. The thing you want to be careful about is when you're running source and you're also like testing out new things, is just because you click source doesn't mean that the environment panel is clean. And so if you want to make sure you're cleaning and starting from a brand new slate, you want to go to session, restart R. And what that will do is clear everything. And then if you click on source, it'll run everything that in this current file, one line at a time. So now that we have 3 lines in our code, we want to be able to save this. So we can save this file using Apple S or Control S. And for now, I'm going to save this in our base working directory, so we're not creating files and folders all over the place for now. One little hint that I find very useful is if you start programming and creating scripts, or even for data sets, if you start your files with a number, you can force the files to sort in the order that you want them to be used in. So for example, loading data as a script and then doing the analysis, loading, because the A in analysis comes before loading, like if you sort the files, that's the alphabetical order isn't necessarily the order that you run the code in. So if you put in 0, 1 loading or 1 dash loading, that'll force it to the top, and then 2 dash analysis, you'll know the order of the scripts that you're supposed to be running it in. And that will save you and your colleagues and other people a lot of headache in terms of like, how do I use this thing? So I'm going to call this for 0, 1, and I'll call this load dot capital R to signify that this is an R script. And now we have our first R script, and you'll see in the bottom right hand corner it says 0, 1 dash load, and we have our R script. All right, so the first exercise that we have is in this data folder, there is a data set called medical data _ tumor growth. And since Peter Higgins is with us today, this is actually coming from the medical data set, R package that he maintains. And what I did was I literally dumped out a CSV for teaching purposes. And so I want you to take this tumor growth _ long data and save that to a variable called tumor. So load the tumor data into the variable tumor. So that is the exercise that I will give about a minute for. And if you have questions, you can post them.
So Daniel, as background for Kelly, she tends to load really, really large genetics data sets and have to do a little bit of cleaning and then can dig into the actual data analysis. But those first couple of steps are very slow and very long. So there's an advantage to saving an intermediate file or using tools like Workflower or Targets.
Oh, yeah. So like I mentioned in the first block or the first lesson or unit, data pipelines, the like very simple way pipelines are created is you're literally passing in an like intermediate data set. And so if you do have a large project, and I do this as well, maybe I will show this like on Thursday when I can pull up a really good example. But if you have, for example, a step that takes a really long time, it's okay to literally have a single script that says like, I'm going to load this data. This thing is like 1 million rows. I only care about like 100 of them, for example. I'm going to load this data, filter on 100, save out only the 100 that I need. And then so the next step in the pipeline doesn't have to spend like the 3 or however long to load that data set again and refilter. And so if you do go back, and so this ties back into your original question, if you have multiple projects, do you have to load each one every single time? The answer is you only have to load it if you want to run that script again from the top to the bottom, in which case you'll just run everything from top to bottom. But if you're thinking in terms of pipelining, and you'll see like when we go to the next section, when we open up the analysis part, we're going to save out a data set in our load, and then we're going to open up a new script, clear everything, and then we only need to load the parts that we need from, the pre-filtering step. So hopefully that helped. It's like a question that has like multiple different ways of solving the same solution. But in general, yes, we're slowly starting to build data pipelines, and the way you build these pipelines is passing off intermediate data sets. And the benefit of that is you're creating this pipeline, so you are in the process of creating something that's reproducible, right? So even if you got something that's from like a genomics data set from the NIH, you download it down, you filter it, and if all you do in R is to like, because Excel for whatever reason like thinks that a genome sequence is a date, you filter and fix things or work with things in R. And then you save out whatever you cleaned or processed. And it could be as simple as I just drop the first like 9,000 rows and then save out a data set that's 100 rows long. And if you do the rest of your process in Excel, then, you know, if R is that new to you, then I would say like that's a pretty good step forward, because you're building the reproducible portion of your analysis, right? Now, if the NIH releases a new data set, you don't have to worry about going manually deleting the first like 100,000 rows. You've sort of reproduced or replicated those results in code. And you'll see more about like starting pipelines when we actually work on the next R script, how you can make sure you're starting from a clean slate. Okay, so the exercise is load the tumor data into the variable tumor. So how do we find the tumor data? It is in the data folder, and it's this tumor growth _long. So we already have tidyverse loaded, and I showed you we can use the read_CSV function, read_CSV, and then we can say data / and then hit the tab key. And then we can navigate to tumor growth _long. Let me make sure that's what I have in my notes. Sorry, that is the wrong one. The one I went was this medical data _tumor growth, that CSV. And that will load up this example data set where we're looking at the size of a tumor for a particular day given their treatment value. And our trick is to load this into the variable called tumor. So we can say tumor gets, which is this arrow. And now if we run it, you'll see on the top right corner, the tumor variable is there, and we can click this, and then it'll open up the data explorer for us to view. One thing I do want to show you is if we do have tidyverse, I believe it also comes with the read XL, like the letter X. So we can say library read XL. And what this allows us to do is it provides us a function that lets us read Excel files. So there is a function in here called read_Excel. So aptly named. And now if we use the same syntax, instead of pointing it to a CSV file, we point to a Excel file. So in our example data sets, we have the same exact data from before, but in Excel format. We can run that, and we can see we can actually read in an Excel file also into R. And so I can also call this tumor_XL. And that will load up the Excel file. And these two things are exactly the same. And so in read Excel, so if we put our cursor to the right of the L and to the left of the open bracket, and then hit the F1 key, or we can say $read Excel in the R console down here. Hitting F1 is a shortcut to open the help documentation for this function. So you can see at the top it's saying, hey, we're looking at the read_Excel function in the read_Excel package. And you can see here we're using the read_Excel function. And in here, you'll notice if you have Excels with different sheets, you can give it a different sheet. You can actually tell it to like skip the first 100,000, like n number of rows, treat missing values as a empty string, etc. So there's a lot of things that these functions will do for you. in addition to being able to read a plain Excel file. So if you do have an Excel file like before, where we talked about like each patient is on its own Excel sheet, you can load those in to R as well. It doesn't have to be a single flat Excel file. Okay, so the next thing that we want to do is, if we're looking at our data set, for example, we have this tumor data set that we are looking at. How do we work with looking at different slices of our data? So in the tidyverse, there is a function called select. And what this lets us do is subset a data set based off of its columns. So you're literally selecting different columns in our data set. The way select works, so in read_Excel, we give it a location to a file in either single quotes or double quotes, that doesn't matter. If we give select, the first thing is the data set we want to select. And then the second option is a column name. So let's pick a column called size, for example. And now if we hit size, and this is case sensitive, you can see that R will take that data set and then only give you that column back, right? And so now if we say comma and then comma delineate, like we also want day and, size again. I guess it doesn't let you do something twice. I guess it doesn't. Group. It will only select the columns that you want, right? So if you have a data set that has 100 columns, but you only care about the ID column and then like some other combination of columns, you can use that as a way to select your columns. If you're browsing around R, you'll notice that some people talk about piping, and they talk about this % greater than %. So that is like shift 5.5 on a US keyboard. Piping. And so there's another way we can write this code, which is selecting tumor from the tumor data set, select the size, day, and group. And this is known as piping. And the way we can rewrite this is, I will write this first. We can take the line of code that I wrote before, which is select tumor, size, day, group, and then rewrite it such that the first thing that it took, which is tumor, comes out and then gets piped into select. So these two things are, from R's point of view, equivalent, and there'll be more benefits of why this syntax notation down here is a little bit nicer. But if you do see this piping notation, just know in your head it's syntactically synonymous with taking the thing on the left-hand side of the pipe and putting it into the first thing on the right-hand side. Okay, the next thing that I want to show you is, we talked about how we can subset the columns. How do we actually go and filter our rows? So the way we can filter rows is there is a tidyverse function called filter. And filter works similarly to select in that the first thing that it takes is the data set that we want to do our filtering on. In our case is the tumor data set. So the question was, how does read_Excel deal with empty cells, missing data in Excel files? By default, if a cell is empty, it will be read in as a missing value from R's point of view. So if it's like, you can still see here the help documentation is still open. If it is a quote, like empty string, like there's nothing there, R has a special value for missingness, which is capital N-A, like N. Yes. So that is R's interpretation of a missing value. And you'll see that in big red letters if R does load up in missing value. And if, for example, this is also pretty common in health data sets where if you're encoding values, there's a difference between like people want to make sure that like that value is actually missing because I know it's missing versus like I am the data person and I forgot to put the value in. You'll see 88s or 99s. And so you can change how R reads in a missing value by changing this parameter. You can say like, hey, treat all the 88s and all the 99s as a missing value. Just be careful because I've done this before in the past and it took me a while to figure out if you have an ID column that's like numbered 1 to whatever and you say like treat all the 99s as missing, you just turn like one of your ID columns into a missing value. But that's much better than control, find and replace the raw Excel sheet, all the 88s, 99s to an empty string because that's much harder to figure out what went wrong than like seeing it in your code. So back to filter. So filtering, think of this as how we want to filter our rows. The first thing it takes is the data set that we want to filter. And then let's say, for example, I only want the rows where the group value is equal to 1. And so after the comma, we say the column, which is the condition that we're trying to talk about, which is group. And then we want this group value equal to 1. And in programming, we don't use a single equal to designate a comparison operator. We use the double equal sign. And so this is saying, is the value of group equal to 1? If that is true, then keep that row. And now if we run it, you'll notice that our original data set, which has 574 values, if we say group is equal to 1, there is now 87 more rows plus the 10 it's showing. So it's 97 rows that has a group value of 1. Right? So there is a difference between a single equal, because a single equal, in theory, you can replace this arrow operator with a single equal, and that's the assignment operator. But in many programming language, the double equals refers to test for equality. And again, we can rewrite this notation using piping notation, saying that we want to take our tumor variable and then piping it into the filter function such that the value of group is equal to 1. And then those two values are going to be exactly the same. If we want multiple conditions, so now I'm going to copy paste this. Let's say we want a value such that the group is equal to 1 and the day is equal to 0. We can specify it with a comma and say, and we also want it such that the day is equal to 0. And then you can see now there's only 8 values left in our data set where the group value is 1 and then the day is 0. And then you can see that these are all of the starting tumor sizes for all of our patients in the control group on the first day. Another way you can use the to say and is to literally use the ampersand key. So that's Shift 7 to type in this ampersand, and that is the another way you can say like and this other condition. And I mention this and operator because you need a special symbol if you want to say or. So let's say we want to filter our days such that the day is 0 or the day is equal to 13. And the way we type or is using this pipe symbol. So this is different from like the pipe operator, which is % greater %. This is shift and then the key above the enter key, which unless you're programming, I very much doubt you've ever hit that key in your life. And this vertical pipe is how we designate or. So now this is saying, give me the tumor give me from the tumor data set all of the values where day is equal to 0 or day is equal to 13. And so now we have across all of our data sets, which there are 60 rows here, the starting and ending tumor sizes across all of our patients, across all of our groups. And you can use different parentheses to sort of make up your own conditional operator as you need. the last thing for before we go on this really short, the next break, is how we can subset both rows and columns. And so this is sort of where using this pipe operator comes into play, because the output of this data set, this function, this tumor pipe into filter, is another data set, right? It's another what's known in R as a data frame. And so I showed you that select outputs another data frame, filter outputs another data frame, and their inputs are also data frames. And so if we, for example, want to select different columns and then also filter on different rows, we can pipe one of the results into the other. And this is where this piping notation starts to come into play. So we can now say, from the tumor data set, we want to select, for example, the group column, the day column, the size column, and then from those columns, or from that new data set, we want to then filter such that the size is, for example, greater than 2000. And so what this did was this is also why people like the piping syntax, because you can really look at the first word in each line and sort of read it like English. So we have tumor, and then the way you pronounce this pipe is then. So it's tumor, then select, then filter. And so that gives you a general sense, a pretty good sense of like what you're doing. I'm doing something on the columns, I'm doing something on the rows. If you then care about the details, you can then look on the right-hand side. And so now we have these three columns that we selected such that a large tumor size greater than 2000. And then you can see like most of these are on the second half of the study. And the last thing I want to show you is saving out our data set. So this is important when we're thinking about building pipelines, right? So we have this tumor data set. We selected by group. So let's say I want to have group, but then I also want the ID in there because that's important, day and size. And then I want to filter on, day is equal to 0 or day is equal to 13. Like, let's say, for example, I only care about the start and like midpoint of our tumor growth data set, right? So I can run this code. This looks good. I can then remember in each one of these steps, just like loading in a data set, we can always save this to a variable, right? So all of this stuff right now, if we look at the top right panel, none of those data processing steps was saved into an R variable yet. And so we can now say filtered gets that. And then you can see now our filter data set is now 60 observations with 4 columns versus the 574 with 5. And once we have this variable and we're happy with it, to build our data pipeline, we can use the opposite of read CSV. There is a function called write_CSV. This takes a data set that we want to write, so that's filtered, and then we can give it a location we want to save this file to. So we can say, before I say I loaded a data set from the data folder, now I'm going to write a data to the data folder. And instead of, we don't want to overwrite an existing file, so we can literally type a new file. So we can say tumor_filtered.csv. And now if we run that code, go to our data folder, you will see that there is a tumor filtered CSV file that we have. And so we'll stop now for a short break to the top of the hour, but this shows you how you can load up a data set, take exactly the parts that you need for the next step in your pipeline, and then save out the file. And now what this means that if this is a really large data set that takes up a bunch of time, you only need to run this when your underlining raw data set gets updated. Otherwise, you have a nice smaller, faster data set that you can work with for the rest of your pipelining, because you have this physical data set on your computer that you can load in on a different file. So you don't have to constantly source this file from top to bottom if all you care about are these 60 observations versus like the 574. So let's take a break to the top of the hour, and then I want to very quickly just go over how we can load in a descriptive calculation, and then that will be enough for today, and then that'll lay us with enough of a foundation for cleaning and processing our data on Thursday. So one question I got in chat was, is there a way to very quickly see the variables or columns in your data set? Yes, there's two ways you can do it. The point and click way, if you click on the little blue arrow in RStudio, it'll give you like the line listing of like the column name and then all of its values. This is sort of useful for like, you know, if you have a data set that's like somewhat reasonable, that this like drop down is useful. You can imagine if this was like 1 million columns or like even 100 columns, this very quickly gets out of hand. So one way you can just, if all you care about is like, I just want to know my column names, there is a function called col names. Like this is not related to tidyverse. It stands for column names, and if you give it a data set, it'll give you back all of the column names in your data set. Because this is a data frame, you could technically can use this function called names, but I guess this is way more explicit because you can think about like there's also row names, and so just to reduce the confusion, you can use column names or names to get the just the column names on your data set. And this is super useful actually because this code, even like names filtered, both of these things give us the same results in our case. It's super useful that it gave us these double quotes, because if you're loading in data from like Excel, especially something that you've put together by yourself, it's also very common, and this has hurt me a bunch of times too, where like, you know, someone put a space at the beginning or multiple spaces at the beginning or at the end of like a column name, so like it properly centers in their data set. But now the actual column is really space, 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 size, space, space, instead of just size. And now all of a sudden you're trying to filter on the size column, but it's not working because the column name is actually 4 spaces size, not just size. So using the column names in this sense is a really good way to figure out like who really like how messed up is this like column name situation because like someone put a space somewhere in there. And you can also see this points back to why having spaces in your column names become problematic, because you can see like I'll do this right here with a simple example. We'll do it with the select example. If I had something like, let's say I had a column called tumor size, which I don't, it's going to tell you I have no idea like what's going on in here. And if you do have spaces in your column name, in dplyr you have to tell it to treat this like literally as this thing, including the space, with a backtick, which is the key to the left of the number 1 if you're on a full size US keyboard. It's not a actual quote, which is like the left of the enter key where your right pinky normally hits. This is like a little, like, it looks like a like a really tiny slash, not like a vertical apostrophe. And this tells tidyverse, or really the select function, hey, treat this whole thing as one item versus like two separate things. And you can see when I wrote that, I get something as an unexpected symbol, because it doesn't understand this space, versus like, hey, tumor size doesn't exist as a column, right? So those are, as you sort of get used to programming, you sort of like convince yourself like these error messages make sense. So that's how you deal with like spaces in your column names. And that's why having spaces ends up being more annoying to work with, because now you literally have to type 2 more characters to deal with the space. Okay, the last thing I want to cover for today is actually doing something useful with our data set after we filtered it. And so I'm going to go to File, New File, and New R script. And we're going to save this as 02 / I'll just call it describe.r. And so it's a good habit to get into that if you start in a new script, you want to go to Session and restart R. And what this will do is it'll make sure that the right-hand panel is completely erased. So nothing from the previous script is carrying over to the second script. And this is important for pipelining, because when you run pipelines, these things are usually run independently from one another. The next step in the pipeline doesn't automatically rerun the contents of the first item in the pipeline. And so the more you can clear your working area between these different scripts, the more independent these scripts become, and then the more this is how you build pipelines. And so because we restarted everything, this script also needs to know how to load up tidyverse. So we'll load that tidyverse function library again. And in our previous example, we subsetted a tumor data set. And so in this example, we can now reload this tumor data set. So we can say something like tumor_subset gets read_CSV. And then we can say data / it was called tumor filtered. Is it called tumor filtered? Yes. And so now what we did in this script is we loaded up the output of the previous script, which was that data set. And so congratulations, you literally built your first pipeline. And this pipeline is, we did some data processing. In our case, that processing was filtering rows and selecting columns. And now we're in the process of the next step, which is doing some bit of analysis. So now if we look at tumor subset, and I can just type in tumor subset and run this by itself to see it, or you can click on the button here to see it. This tumor subset is the data set that we're working with. And so now let's think of some kind of statistics that we want to calculate from. We want to work with, let's look at the average size of all of the tumor sizes on the first day, right? So maybe our question is like, hey, is there a difference between day 0 and day 13 in our tumor sizes? Well, we first need a value for day 0 first. And so we can do what we did before. How do we get, the size for day 0? So that's using the same filtering, selecting procedure as before. So we can say tumor data set. First, we want to filter such that our day has a value of 0. So I can hit and run that bit of code first. And this looks pretty good. We have a data set that seems to just have all zeros, and that's what we expect. The next thing is a new bit of information. Before I showed you select size, and you can see it gave us a column of variables. But this now goes into a little bit more of like a math notation of like what is a matrix versus what is a vector. So you can think of a column in a data set, or a data set. our tumor data set, you can think of has 2 dimensions. There is like the columns as one dimensions, and then the rows as another dimension, right? And even a data set that's 1 column still has a dimension of 1 for the columns, and then however many rows in the other dimension. And so a lot of these statistical functions don't take these 2-dimensional objects. They only take 1-dimensional objects, right? So if I'm trying to say like calculate the average between 1, 3, and 5, I'm giving you the values 1, 3, and 5, not this 1 doesn't have like 2 coordinates associated with it. And so instead of select, the tidyverse way of saying, hey, I want you to take this column, but treat this as a column of individual values versus a actual like 2-dimensional column. And so if we look at the difference between the outputs here, hopefully that made sense. One actually looks like a column of data, and the other is just a sequence of data. And so once we have a sequence of data, we can then say like, hey, now we can use the built-in mean function to calculate the mean of the sizes such that the day is equal to 0. And then in regular English terms, this is the average size of all of our, is it all of our patients? Yes, across all of our patients on day 0. So this is the baseline tumor size across everyone. So that's good, but that's across all of our patients, but our data set contains different treatment groups. So now we can say like, okay, we don't want the, in biostats term, it's called the crude estimate. We don't want the crude baseline tumor size. We actually care about them broken up into different, like by the groups that they were assigned. So in the filter statement, we can now say, filter where the group is 2 and also where day is 0. And then you can see that I believe group 2 is a treatment group. You can see that this tumor size is slightly smaller, is it? Slightly larger than the overall tumor size. And then we have a bunch of these groups. So we can say like, okay, compare the value for 3. So treatment 3's got like smaller tumor sizes. Treatment 4, we have this all the way up to 4. It's a little bigger than that, et cetera, et cetera. But it's not really, you can sort of see like, okay, we're starting to do the data analysis portion of our working with our data set, but now we have this problem of like, okay, for every single group, if I really want to calculate the starting treatment value, I have to like copy and paste that and change a single value. That becomes a problem, right? So let's say there's like 100 treatment groups. It is now infeasible, or it is feasible, but now you're highly error prone from copy and pasting if you've like changed the correct value, right? So in Excel, we fix this with a group by operation, right? So before I go there, let's say, for example, I have my tumor data set. Remember, we can say pull the group value. So these are all of the group values. So we can see it's 1, 2, 3, and 4. There is a baseline R function called unique. And you can see like there's 4 unique groups here. And so like this is somewhat feasible. We can copy and paste code 4 times. That's not that big of an issue, but you can imagine if this becomes 100, that does become an issue. So we can do that, like combining, splitting of our data sets, performing some calculation, and then combining the results all in a single go. And in Excel, that's called a group by operation. Like in Excel, there's a little button called group by, and then you can drag and drop how you want your data split and how you want what statistic you want calculated. Okay, so let's say we want to perform this group by operation. First, we only care about baseline values. So we can say filter such that day is equal to 0, right? So we can build this pipeline, this bit of pipelining code one step at a time. And then we can say, hey, I want a calculation done, but I want the calculation done for each unique value of this other column or this other set of columns. And so tidyverse comes with this function called group by. And we can say, so group by group. So we're going to say for each unique value of group, I want you to do something. And if I run this code now, it doesn't really do anything other than if we look at the output from the previous example, which just says Tibble 3 rows by 4 columns. The next one really says, well, it's a Tibble 3 by 4 columns, but now we have group. It is going to be group by the group column, and that group has 4 values in it. But it doesn't actually do anything because we haven't told it to do a calculation. And so the next step is going to be now perform this calculation. And so the syntax is going to be a little wonky. I'm going to write it first and then explain it to you. Okay, so if I pipe, so at the end of the day, we want this value here, this data set here, which is the average tumor size such that from day 0 for each group all in one little data set instead of 4 or 100 individual values. And the way we specify that, the keyword here is group by, and then the next line it says summarize, so we're doing a summary statistic. And then we're calling the mean function just like before. And then we're assigning that to a column called average size. So this average size shows up here. And then for each unique value of group, put that new mean calculation there. And so this last line is pretty dense, but that's essentially what's going on. And you can now run all of these summary statistics without having to click a bunch of buttons in Excel, right? A thing about summarize, you use summarize with functions that take in a bunch of like multiple values as input and only a single value as an output, right? So mean is a function that can take multiple inputs, like 1, 3, 5, and then it returns a single value, which is 3 in our example. Right, so that is a function that takes multiple inputs and only outputs a single value. That's what you would use in this summarize block. So another thing that we can say is SD size is the standard deviation of size, right? So standard deviation is also another function that takes in multiple inputs and then outputs a single value. Contrast this with something like a centering function, like taking the z-score. The z-score is a function that takes in X number of input and also X number of output. And that is not something that will work within summarize. But if you're trying to calculate like, oh, what is like Q1? There is a function called, I think it's quartile, quarters? No. This is when live coding becomes like all weird. But there is a function that lets you calculate quartiles, and you can say like, what is the 25th% or 75% quartile of our data? Quartiles is another function that takes a bunch of things as input and a single value as output. Okay, so I just want to end the class there. I know there's usually like a final exercise, but we'll do that as a review on Thursday as people roll in. And I have a summary slide deck, which I guess I will go over today, just in case people can't make okay, so yeah, so we'll call that for today. So we'll leave everyone off a little bit early. There is a few, I guess, administrative things. If you can, there is a link to the materials that we covered today. If you can, I believe you still qualify to take the pre-workshop survey because we're not done yet. So please go ahead and take the pre-workshop survey if you can before the end of Thursday's class. That would be great. So you can take the post-workshop survey. And for the people that are want to know more about like additional resources, this is a slide deck that I'll represent on Thursday afternoon. But like I mentioned in the very beginning, there is a entire ecosystem of people who want to help you go through this. So there is the R+RStudio book. This is a resource that's free and public, and it's online. That goes into more details about every single function that I will cover in the next 2 days, or on Thursday and today. There is this resource called the Big Book of R, which is the current materials that we're going through is a set of R lessons that are specifically geared towards like clinicians who want to get into using R as a programming language. But that resource has a bunch of other domains. So if you're really interested about like making maps, there's like a link to the R map book that's also free for you to use. If you're into using genomics data, there is a link to like working with genomics data in that Big Book of R stuff. Other places where you can ask for help, there is an R4DS community where you can join the Slack group for r4ds.io/join. They do have multiple office hours in a week. There's also book reading clubs that you can join. There is a Tidy Tuesday thing going on in Twitter every week where one of the best ways of getting used to or learning how to program is really to do something with it. And so if you're out of data sets or you can't use a data set for HIPAA reasons, you can use the data sets posted on Tidy Tuesday. So today is Tuesday, so a new data set was released today, and you can play around with that data set. And if you don't know what to do with them, there is a person named David Robinson who literally streams a 1-hour block of how he like analyzes a data set from the first time he looks at it. So it's actually really cool watching someone who's like an expert using the tools to get something cool out of it using R. If you are a lady or identify as one, there is the R Lady Slack group, which you can join. And if there are a lot of very helpful people in that Slack group to help you with your R questions. And then since Peter is here, he runs the R Medicine conference every year. And there is the R Medicine Slack group that you can also join for help, concerns, questions about this stuff too. And if you ping me in any of those Slack groups, minus the R Ladies one, I can probably find you, or you can probably find me there. So I would leave that for today. And then we'll pick up on Thursday with processing data and an intro to visualization and fitting models as a way to sort of tie everything together. Yeah, so I'll be sticking around for like the next couple of minutes or so until everyone really leaves. So if you have any questions, just let me know or post them or message us, and then we'll see you on Thursday.